Okay, for people who are coming from that side, there are a lot more seats. Well, not a lot more, but more seats on this side if you're trying to squeeze it up there. Come on this side. And further down. Now I'm going to get started. Can you do the slide to be static? Okay. Okay. As people are finding their seats, we're going to get started. Can you hear me? Much better. Okay, thank you. So my name is Vicky Calogera. I'm a professor in physics and astronomy here at Northwestern, and I'm also the director of SIERA, the Center for Interdisciplinary Exploration and Research in Astrophysics. So I'm excited to welcome you tonight to SIERA's Astronomy Night Out. This is a multi-part event. We have a lecture. I'm going to tell you a little bit about it in a minute. But also we have a large number of exhibit tables outside our lecture hall with hands-on activities. And you'll have plenty, some of you have already interacted, but you'll have plenty of time to interact with the tables after the lecture. Also, from 8:30 to 10 p.m., we have observing. We need to wait for dark to come, to settle. And 8:30 to 10, we're going to have observing at Dearborn Observatory, which is about less than 10 minutes walk from this location. And from 8:20 to 9 p.m., there's going to be walking groups, guided walking groups, departing this space every 10 minutes, okay? So you can take your time and spread it around so you don't have to wait too much in line at Dearborn Observatory. I'd like to thank almost 20 people worked to make this event ready and prepare it. All guided by leadership at SIERA, and especially our Director of Education and Public Outreach, James Schottelkotte, who I'm sure is somewhere here or outside. There, I see him at the door. But he has a lot of support from many members of SIERA. And I want to also tell you that the whole event here is going to be recorded, so I need to let you know about that. At the end of the event, of the lecture, you're gonna see that there are surveys, or actually, I don't know, no, the surveys are not on the seats, but there are mini surveys that you can fill in, and I would like to ask you to fill them in if you want to be included in our email list where you can get announcements for more events from SIERA. Now, if you also want to discover how to walk away tonight with one of these gorgeous SIERA t-shirts that you see around, that the design has been designed by one of our graduate students, Kirsten, and she's somewhere here. Then if you want to walk away with one of these t-shirts, then you need to not only fill in the survey, but do something else. And if you do that something else, you're also going to enter a raffle for a very special prize, okay? So this is logistics. All right. Now my speech is starting. I thought I was going to get a laugh, people. All right. So Astronomy Night Out has been happening for a few years. And public lectures from SIERA have been happening for a few more years. But tonight's event is really special, to us at least. It's a milestone for SIERA because this year we're celebrating 15 years since SIERA was established. It's hard to imagine for us who have been at the beginning of SIERA that 15 years have passed. A lot of things have changed, But there's one thing that has not changed: our excitement and anticipation when we hold events like this, and we can interact and connect with our local communities. So thank you all for being here tonight. I have been at Northwestern for 25 years. I came as a baby faculty, and I feel privileged that with the help of a lot of colleagues through the years, we created what now is a top astronomy program in the country, top 10, top 5 in some categories. And this has happened with a lot of work, and we are now in the same group of programs that have been top tier programs across the country, with investment at their home institutions for over 100 years. We've done it in 15, 20 years. How did we do it? Well, we did it with passion, vision, dedication, optimism, amazing people working very, very hard, and having them by our side. And we have done it with recognition and support from our home institution, Northwestern, but also philanthropies. We feel gratitude and pride to be part of Sierra. And we can't wait to see what comes for the next 15 years. We started from, well before I was here, or any of us were here, with observations with the telescope at Dearborn Observatory. Telescopes are our labs for astronomy. We cannot do anything without data from telescopes. Now our present is driven by the fact that we have access to the best telescope operating on our planet, and that's the Keck Observatory, but also access to many other telescopes, both on the planet and in space. And just this year, Northwestern made the historic decision, in partnership with Sierra, to become an actual construction partner on the next generation telescope called the Giant Magellan Telescope. This is the kind of trajectory we have been following the past 15 years. But astronomy is beyond, Sierra is beyond astronomy. Our partnerships and our special character in the nation is our connection with other disciplines and our approach for how we solve the problems that we are choosing to work on. So we have partnerships with computer science, artificial intelligence. In fact, our reputation in artificial intelligence is something that led to being invited to join the Giant Magellan Consortium, but also engineering, also the arts, communication, and education across the university. And also, we are committed to education and public outreach, education from high school, from undergraduate, of course, graduate education, and also public outreach with numerous events like the one tonight. So, of course, I can't wait to see what the next 15 years will bring us, and I hope I'm not the one standing always up here for the next 15 years. Now, our speaker, Professor Emeritus Dave Meyer. Why Dave Meyer for this special event? Well, Dave Meyer was one of the inaugural founding co-directors of Sierra, and many other things that I'll come to tell you about. He joined Northwestern 38 years ago. In 1987, he got his PhD in astronomy at UCLA. He spent a few years, 3 years, as a McCormick Prize Fellow at the University of Chicago, that other little university around us, the Enrico Fermi Institute, and then he joined Northwestern as a faculty. Over his years, his most important role was being founding co-director of Sierra. But He was also department chair, chair of the Department of Physics and Astronomy for 3 years, and then for 14 years, director of our Dearborn Observatory. His research has focused on spectroscopy of stars and quasars and the gas in galaxies in between stars. And he's world-renowned for his expertise in chemistry and in revealing the structure and conditions of clouds that form stars in galaxies. I'm sure we're going to hear some of that. For 30 plus years, he basically used almost every telescope on the Earth, including the Keck most recently, and in space, most often, it's not common to use the Hubble Space Telescope and even the James Webb Telescope most recently. He's also a superb and legendary, really, teacher. He has won every teaching award that exists at Northwestern, including the highest honor for a teacher at Northwestern, the Charles Deering McCormick Professorship of Teaching Excellence. In addition to that, I forgot to, I did it. In addition to that, he was discovered by the teaching company and for the series of the great courses, and he has developed 3 great courses related to Hubble Space Telescope, our Milky Way, and a tour of the whole universe. So you may get the opportunity to win something like this if you pay attention at the end of the lecture. Now, I'll finish by saying Dave is not just a fitting speaker for tonight because of our anniversary as a founding co-director of Sierra. Dave, to me, as a new faculty, very quickly was not just a colleague, but became a very influential mentor. Not so much on my research, our fields are not very close to one another, but more about, for me, learning how to become a professor, how to become a mentor to other students, how to think about leadership, and how to think about how to make a place better, and think about well beyond my own little corner of my universe. It is a great honor and privilege to invite Professor Dave Meyer for his lecture. Thank you, Dave. And yes, I took a long time, so you will have a little extra time. I'm sorry, but I had to say it.
Okay, well, we're just going to have some fun.
Okay.
All right.
You don't need this.
Don't need that. Can everyone hear me? Great. Well, hi, everyone. Thanks for coming. And we're going to make it darker in here. Indeed, we're going to make it really dark in here. Maybe not. We'll save the last bank for a little bit later. I'm really happy to talk to you this evening about the Milky Way. Now, one thing you should know right off the bat, if you want to go look at the Milky Way with your naked eye, this is about the worst place to be in Chicago and Evanston. The sky is just too bright, okay? It's just too bright to see something like this, where we are up here. Let's get this. This is Yellowstone National Park in Wyoming. That's a very dark site with really dark skies. And dark skies are really hard to find in the continental US these days, okay? But what as I begin to talk about the Milky Way, I want you to think about, I'm going to give you a homework assignment right at the beginning. This summer, when you go on vacation somewhere, hopefully you'll go somewhere with dark skies. Where are dark skies? National parks, often in the western part of the country. And if you're staying close to home here, a day's drive away, you go up to northern Wisconsin. I'm a native Wisconsinite, so I may talk a little funny, but that's where you go. Northern Wisconsin, you go to northern Michigan, and the skies are really dark. Okay? So if you manage to do that this summer, what I want you to do is wait an hour and a half after sunset at least, then go outside on a night there's no moon and it's absolutely clear, and allow 20 to 30 minutes for your eyes to get dark adapted. And if you have never done something like this before, you will be astonished at what you will see. Under those true dark sky conditions, if you decided, I got nothing better to do than that, I'm going to count every individual star I can see in the sky, you come up to about 3,000. Okay? In the Chicago sky, even the best time of night, best time of whatever, maybe a dozen, 2 dozens, but up there. But in addition to counting stars, the thing that'll stand out from that kind of a view is just like you'd see here in Yellowstone. You would see this Milky Way, this stretch of light stretching across the sky. Okay? And wherever you go at one of these national parks in the northern U.S. or Wisconsin or upper Michigan, it'll have this kind of a structure, and you will see, follow the Milky Way across the sky to the south. And you will see this bright patch of the Milky Way. And you will be able to see this with your eye. You won't need a telescope. You will not need binoculars. The Milky Way, under those conditions, will be bright enough to not only see this diffuse glow, but you'll see these dark patches amidst it. And you'll see, aha, that's not missing stars. Those are like clouds, okay? And what you're looking at in this direction is the center of our galaxy, okay? And what we're going to focus on in the beginning of this talk, we're into it a bit, is studying these clouds. These are clouds of stardust and clouds of gas, interstellar clouds of gas and stardust. The gas is mostly hydrogen, 90%. 9% of it's helium, and 1% is every other element in the periodic table. The stardust are little solid particles. Little solid particles, magnesium compounds, iron compounds, etc., silicon compounds, and they block the background starlight. So we can't see to the center of our galaxy because of these clouds. So if you go out and see this with your own eye, it's one thing to see it in a picture. It looks beautiful. But to see it with your own eyes, you will begin to realize, this is my home. I live here. This is where I live, in the Milky Way galaxy. When I look in this direction, I can see the center of our galaxy. You can't see it exactly, but you can see in that direction. And you can follow this path. And when you look at this path of the Milky Way across the sky, and you see the bright parts, and you see these dark patches amidst it, you're looking at the stellar backbone of our disk-shaped spiral galaxy. There are on the order of 300 billion stars in our galaxy. Most of them are along this Milky Way. Now, these stars here above and below the plane are also in the Milky Way. They're in our part of the Milky Way galaxy. And one of the most difficult things in understanding the Milky Way is we live in it. Okay? How can you get a picture of something that you're inside of? Okay? And we'll be coming back to that theme a lot today. But where we're really going to go is with the space telescopes, Hubble in particular, and the James Webb Space Telescope. We're going to visit some of these clouds. And the reason these clouds are important, the big, thick, huge clouds, many light years in size, hundreds of thousands of solar masses, that's where stars form. Okay? And the Milky Way is cranking out 10 stars per year on average. You might say, 10, that's not much of a factor, but this is a star. It's not easy to make a star. 10 stars per year. And how does this work? How is it our galaxy cranking out these stars? I'll give you a sense of how that works and take trips into these clouds with the Hubble and the Webb telescopes. And another thing, just as a background, when you look up at the sky and wonder about it, and indeed, when you look at the Milky Way like this instead of in a book or in a slide, you will remember it. Particularly if you've never been to a truly dark site and looked up at the stars, this is something you will remember. It's hard to forget it. Is understand that along with all these stars in our galaxy, 300 billion some stars, we think there are at least that many planets out there too. 300 billion planets. And among those, there must be billions of planets the size of Earth, mass of Earth. And there's good reasons many scientists think that life is common in the galaxy. We haven't found it yet on other planets, but we have reason to think that it's common, and some of it may be intelligent life. And to kind of bring a connection between other life civilizations in our Milky Way, if possible, if they have a night sky, if they live on the surface and they look at the night sky, they'd have a view like this too. It would be from a different perspective, but they'd see the same kind of thing. They'd see a starry sky and they'd see a band of light across the sky signifying the disk of our galaxy. So if you ever want, we'll be talking about things tonight. We're expanding your horizons, so to speak, okay? And if you ever get troubled by things, there's one really good, looking up at the night sky at a truly dark sight, it really is a good thing to do. So I recommend it highly. So we have tonight's astronomy night out, and I'll get back to that in a second, but this is something to think about, astronomy night out and a truly dark sight. So before we get into all of this big picture stuff, we ought to come back closer to home and get started so we get all kind of on the same basis here. Now hopefully you folks will go visit the Dearborn Telescope, which is just southeast of Tech this evening. And it has a telescope with an 18.5-inch lens. And I said the skies are miserable here for looking at the Milky Way, but for looking at bright objects like like planets and the moon, et cetera, and some stars and star clusters, you get a great view through this telescope. And tonight, if all goes well and the fog stays away, Mars would probably be a target that people will be looking at, okay, at the telescope. My favorite target with this telescope, though, is Saturn, okay? With this telescope, this is what Saturn looks like. It has rings. I can tell you from long experience teaching at Northwestern, I would encounter students who would have religious experiences. They'd go through this telescope and they'd say, we're going to look at Saturn. They see a bright point of light in the sky, and then they look through the telescope and say, it has rings. Yeah, it's really up there. It's one thing to see Saturn in a book, a picture of it, but when you see it with your naked eye, what? One student was so incredulous, wait a minute, this is fake. You painted it on the lens. No. So he moved the telescope off. After 10 minutes of long discussion, he began to believe it was real, and he was stunned. Okay? Unfortunately, Saturn isn't up this evening. It comes up very early in the morning tomorrow. But at some point later this summer, when Saturn is accessible, we have public nights with the Dearborn Telescope every Friday night. This is something to come back for later this summer, because Saturn is truly something special to see with the Dearborn Telescope. Well, let's think about, just do a little inventory of our solar system. I'm sorry, the NFL's announcing their football schedule tomorrow, so I'm thinking football. So I put up the planets in the solar system on a football field with the surface of the sun at one goal line and Neptune at the other to give you a sense of the scale of the solar system. The four rocky planets, Mars, Venus, Earth, and Mars, they're all deep in the red zone inside the 5-yard line, okay? And we just talked about Saturn. Saturn is about 10 times further away from the sun than the Earth is. And since we're talking about big distances in this lecture, I'm going to use light travel units. And in terms of light travel units, the distance between the Earth and the sun is 8 light minutes. It takes 8 minutes for light to get from the sun to the Earth. Saturn is 10 times further away. It takes 80 minutes for light to get from the sun to Saturn, okay? Now, these kinds of distances, one of the great things about these kinds of distances in terms of exploration of the universe is we can go there. We can build spacecraft that can actually visit these planets, fly by them or go in orbit on them, or even maybe land on them, and give us an up-close view. Okay? Now, it takes some time. We've gone to Saturn in particular to get an up-close view with the Cassini orbiter. It takes a while. We launched it in 1997. It got there in 2004 and flew around the planet for something like 13 years. And we got amazing photos like this one. And here I'm going to make it totally dark. We're getting dark adapted in here now. Okay, so now this is, you cannot get a picture like this from the Earth. This is a picture taken by the Cassini orbiter where the sun is behind Saturn. We're seeing Saturn eclipse the sun and being lit up from behind. And we see these rings, these amazing rings, to give you a sense of scale here from one end of the rings to the other. This is about 70% of the distance between the Earth and the Moon. Okay, Saturn itself is a radius 10 times that of Earth. It's a gas giant. So these rings are amazing. The rings consist of ice particles ranging from pebbles to boulders. Now, if you look at this, you'll see this dot here. And you say, oh, there must be a speck on the photo. No, that's Earth. As viewed from Saturn, this is Earth. Okay, this is another thing that kind of puts things into perspective. Okay, and that's one of the most important things we've learned by sending these spacecraft to other planets in our solar system, is not only to study these other worlds, but to get a sense of the Earth in comparison, and what does Earth look like. You remember how the famous Earthrise the Earthrise over the moon taken by the Apollo astronauts made such a difference, people thinking about that. And this is one of the most beautiful photos Cassini took of Saturn. Now you think about this, oh, we're exploring the solar system, let's go out further. You know, I didn't mention Pluto, okay? We've sent probe past Pluto. Pluto was demoted to the dwarf planet regime about 2 decades ago. I don't have time to get into that. That's another topic entirely. But some of those very early spacecraft that we sent to explore the solar system initially are now beyond the limits of our solar system. Voyager 1 was launched in 1977. It's now 23 light hours away, okay? Much, much, much further away than Saturn. And it's moving fast. It's moving through space at 17 kilometers per second. That's 17 times faster than a rifle bullet, okay? How did it get going that fast? By going past Jupiter and Saturn. It got a gravity assist to boost its speed. So just imagine something that's traveling 17 times the speed of a rifle bullet. You say, okay, well, we can do this. We could explore these other stars now. This is great. Well, here is our stellar neighborhood. Here's the sun. The nearest star is Proxima Centauri. It's a red dwarf star, small star, but it has a planet around it that might have liquid water on its surface. At the velocity of Voyager 1, if it was going in the direction of Proxima Centauri, it would take 75,000 years to reach it. It's 4.25 light years away. Okay? The bottom line here is if we're going to explore the galaxy, if we're going to explore the Milky Way, we're not going to do it with spacecraft. We don't have any Starship Enterprise. We don't have any Stargates. It's going to be many generations of ever before we can explore the stars in our galaxy by going there. And this is just the nearest part around the solar system. And also notice the huge amount of space between stars in the solar neighborhood. Okay? There's one thing I always tell my students. Sometimes we all get in embarrassing situations and you wish, I wish I was anywhere else in the universe. Never wish that. Anywhere else in the universe is dark and cold and there's nothing there. It's really a never wish. We're in one of the best places you could ever want to be on the surface of Earth. This place was built for us. Okay? Space is empty, dark, and cold. Okay? Next, let's take a picture going beyond this local environment of the sun now. Let's take an idea of what our Milky Way's total size is compared to a view of the Milky Way on the sky. Okay? The sun is located 26,000 light years from the galactic center. The sun orbits the Milky Way at a speed of 220 kilometers per second, 220 times the speed of a rifle bullet. It goes around the center of the Milky Way. But it takes, to make one orbit, takes the sun about 230 million years. Okay, it's a big galaxy. Okay, and this disk, the Milky Way, and this is a way to make a comparison here of the Milky Way you see on the sky. If you do this experiment this summer and you find the center of the Milky Way, you're looking in this direction, but the perspective is here you are on Earth around the sun looking toward the galactic center, and what you're seeing is around it from the side. Okay? Just to give you a sense of perspective. And what we're going to do is we're going to fly into some of these clouds to see how this star machinery, this star formation machinery works. And what are we going to use? What are the telescopes we're going to use to go on this adventure? We've had a lot of ground-based telescopes over the year from which we've learned a lot. But there's 2 telescopes in space that we've launched. One in 1990 and one very recently in 2022 to really push the envelope of how we can view the universe. The Hubble Space Telescope was launched in 1990. It's the size of a school bus. It has a mirror that's about 2.4 meters in diameter. It flies at low Earth orbit at about 580 kilometers. and it makes one orbit around the Earth in 96 minutes. And it's the purpose for putting Hubble in space, its main objective was to image the universe with a resolution on the sky at least a factor of 10 better than any telescope we could use on the ground. You see, from the ground, we have this miserable thing called the atmosphere that we need, but it's miserable for astronomers because the atmosphere is always turbulent, it's in motion, and high-pressure systems, low-pressure systems. And the stars twinkle. You say, that's beautiful, that's wonderful, that's romantic. It sucks for astronomers. We don't want stars twinkling. They make things fuzzy. We want to get sharp pictures of what the universe looks like. So one way to do that is put a telescope in space. The only disadvantage really is it's very expensive. To date, the Hubble telescope has cost American taxpayers circa $15 to $20 billion. Okay, launched in 1990. There were a few problems early on, et cetera. We needed the space shuttle up to put it into low Earth orbit, and the space shuttle went up to fix it several times, and it just, as we'll see, has revealed some amazing photos. Now, and another reason that we launched Hubble was to look in the ultraviolet part of the spectrum, which doesn't get through the atmosphere. So Hubble, this is about the size of the Hubble mirror, and the Hubble telescope was designed primarily to look at the optical, but also at shorter wavelengths, the ultraviolet part of the electromagnetic spectrum. But Hubble couldn't see too far into the infrared, the heat radiation of the universe. To do that, and to do it really well, astronomers came up with the idea of building and launching JWST, the James Webb Space Telescope. The James Webb Space Telescope was launched in 2022. It was designed to study the universe in the infrared. The main reason, there are a couple of really key reasons for launching JWST, was to look at the very earliest galaxies in the universe, the youngest galaxies, looking as far back as we can into the history of the universe shortly after the Big Bang 13.8 billion years ago. Those first galaxies, their light would be redshifted due to the enormous distance from the optical part of the spectrum and the ultraviolet into the infrared. Hubble can't see the first galaxies in the universe. They're too faint and they're moved their light too far to the infrared. So we built this telescope with across 6.5 meters in diameter across to do this. And we launched it into an orbit far from the Earth and the Moon at a distance of 1.5 million kilometers from the Earth at a stable gravitational point called the Lagrangian 2 point in space. We didn't need much propellant to keep it in station keeping. And we expect the lifetime of James Webb to be on the order of 20 to 30 years out there. To give you a sense of scale, this sun shield here is about the size of a tennis court. And by putting this sun shield here, it blocks the heat from the sun and the Earth, all coming from one direction. This basically orbits the sun along with the Earth. So adding this to our arsenal now, we have these two powerful telescopes. Now, some folks thought after we launched the Webb telescope, like, okay, that replaces Hubble. It does not replace Hubble. It augments it. Webb does stuff that Hubble can't do, look in the infrared. Hubble does stuff that Webb can't do, looking in the ultraviolet and in the bluer part of the optical spectrum. Okay. So these are our two big tools in our space-based arsenal for studying the universe. So if I want to study star formation, where's a good place to start? Well, the Eagle Nebula has been known for a long time. Indeed, I mean, I'm ancient, and a few of you may remember way back 60 years ago, there was this show called Lost in Space. Okay, this was Apollo time, everybody excited about space. Before Star Trek even, there was Lost in Space. At the premiere episode of Lost in Space back in 1965, 60 years ago, they showed these guys spacewalking, and in the background, they used an old Palomar Observatory photo of the center of the Eagle Nebula. Okay, and that was in that show. Now, when we look at it, this region again with our modern ground-based telescopes, not huge ones, but smaller ones, we get this beautiful picture. And to give you what you're seeing here is this photo is like 80 by 80 light years across. It's big on the sky at a distance of 7,000 light years. Okay, and you look at this entire picture, it's a cloud. It's a big, massive, giant molecular cloud with hundreds of thousands of solar masses of gas and dust. And you say, what about these stars here? These are stars that are in front of this cloud. Inside this cloud is where stars are being made. Okay? And the first stars, the first stars that formed inside this cloud, a number of them were these, as we'll talk about in a few minutes, huge stars emitting tremendous amounts of radiation, ultraviolet radiation with very strong winds. And they're basically excavating the interior of this cloud. And they blew a hole in it, about 20 or so light years across, so we can look inside at optical wavelengths and see what's going on in there, see the machinery of star formation. But the problem with doing it from the ground, we still had our nasty atmosphere making things fuzzy. So in terms of the photo that, the first photo that Hubble revealed to us in like 1995 that really caught everybody's attention, including mine, was zooming in the Milky Way, right going to one of these clouds, looking at that Eagle Nebula, going right into that hole in the Eagle Nebula to see what it would find. And so here what we're doing is we're zooming in into one of these clouds. Remember, one of these clouds, just in the cloud, you can't see. Optical light doesn't get through. But here is this hole. And now with Hubble, we can zoom in and get sharper and sharper and see the nebulosity around the hole and zoom in on these pillars, as we'll see right here, going in further and further to actually see the detailed structure in these columns of dust and actually peer and see the very birthplaces of these stars. And it was astonishing. I remember this photo came out in 1995. I had never seen anything like this. This was a wake-up call for astronomers and the public. Look what this telescope can do. Look what you can learn about the universe when you study it at high resolution. And you'd see these little stalks with stars at the tip. Okay, what's going on here is between these, why are these pillars here? Well, these are the densest parts of the cloud. And what's happened, the older siblings of these young stars just kind of coming out of their dusty cocoons, the radiation and winds from their older siblings is blasting apart the dust now, taking away the matter from which a star can form. Now, the way this works in one of these clouds is you have one of these giant molecular clouds form up, and through various kind of perturbation, pieces of the cloud would begin to collapse due to gravity. These clouds are very cold, especially in their centers, and they collapse. And forming a star takes a long time. It takes about 1 million years, okay? Somewhat less for the more massive ones. And the cloud collapses and collapses and collapses. It takes a long time, but it gets hotter and hotter in the inside. And eventually it reaches a temperature and pressure, something in the order of 10 million degrees inside that collapsing core. A star can turn on. Nuclear fusion engines in the core where you fuse hydrogen into helium and make energy, and a star is born. Okay? And so this has been going on for millions of years inside this nebula. And now there's a breakthrough, and we can see this going on. And we've learned from these kinds of studies with Hubble, and not just Hubble, but the Webb telescope came along. And now we got compare the optical view of the pillars of creation is the term that the NASA PR folks gave this. And this is the optical view, and this is the near-infrared view. You say, whoa, those are kind of different, right? I mean, what's going on here is at infrared wavelengths, the radiation can pass through the dust. The dust doesn't block infrared as well. So you can see many, 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 many more stars. You can see through some of this thick dust somewhat better. To give you a sense of scale here, the length of this tallest dust pillar is 4 light years, roughly. That's the same distance between the Sun and Proxima Centauri, whereas the distance, where there's like not much of anything in our neighborhood. Here, you have this tall dust pillar where there's literally dozens of stars being formed out of this dust pillar right now. So the important part of doing this with Hubble is zooming in, and now with JWST, is we can really begin to truly see the star formation process at work at these wavelengths. And in addition to kind of a near-infrared picture with Webb, we also get this really cool picture with, you go further to the infrared, you can kind of see the radiation from the dust itself. And this particular picture is designed so that the bluer color here reflects the warmer dust, and the redder color fixes to the cooler dust. And here we're actually seeing some of these we don't see stars so much anymore because stars typically don't emit much radiation at mid-infrared wavelengths unless they're inside a dusty cocoon heating up that dust. Then we can see that. So the important thing to realize here is with these looking at different wavelengths in the star forming region, we can begin to put together a picture of how this process works, looking at it at different wavelengths. Now the whole idea of this game, of course, this isn't something you can like, oh, I'm going to go use Webb tonight and actually watch the formation of a star in this cloud. No, it takes that way too long. But the way astronomers work is look at different clouds, see how star formation works at different times, and you put together a picture by breaking down a process that occurs over millions of years by looking at different stages in different clouds and coming up with a theory that fits them all. And one of the really neat ones to look at in terms of a cloud forming stars, where you can get an idea in a later stage of how this evolution works, is the star cluster Westerlund II. It's about 14,000 light years distant, and this image is 30 light years across. To give you a sense of timescale, if you were actually in the vicinity of Westerlund II right now, at this moment, and you look back at Earth, what would you see? You'd see an ice age. Right where we are right now, there's a glacier about 1 kilometer high. That was what this place looks like 14,000 years ago. That's what you'd see tonight if you were in Westerlund II. Once again, thinking about the scale here. But even so, 14,000 years on the time scale of forming a star, that's nothing, okay? The point is, you don't have to worry about these light travel effects so much when you're thinking about comparing different star formation regions. So you see this cluster of stars have formed, and this particular cluster is one of the most luminous star clusters in the universe. It has a number of stars that are extraordinarily massive, putting out tremendous amounts of radiation with very high winds. And what's fun to do with this, the PR gurus at the Space Telescope Science Institute figured out a way. Let's fly in. So here's a way to actually think about this, flying in and getting more of a three-dimensional picture of these dust pillars. You see, it's not just in one star formation region. You see this in multiple star formation regions throughout the galaxy. And you get a sense of this as we fly through this nebula toward the star cluster. And the star cluster itself, as we zoom in, all the stars appear kind of reddish here. That's not so much because of the stars themselves, but there's still this veneer of dust, and dust blocks blue light more than red light, and it makes the background stars at optical wavelengths tend to look more red. Okay? So when we look at and this star cluster is only about 2 million years old, we can look at the stellar census of the stars in that cluster and begin to think about the different types of stars we see. And here's some of the characteristics. The really monster stars are the O stars. They're the most luminous by far. One of these O stars can be as luminous as like hundreds of thousands of suns, and very hot, temperatures more than 35,000 degrees. And a very key point is they lead very short lives. They live typically only for a few million years. And there aren't many in the galaxy. In the entire Milky Way, there's only about 20,000 O stars. On the stellar classification scheme, we consider these basically are the James Deans of the stellar world. They live fast and die young. Okay, so this is, and they really have a lot to say about shaping the interstellar medium in our Milky Way galaxy. Where's the sun on this? We're just a happy G-star. Okay, a G-star is, has a lifetime, which is important for us, of about 10 billion years, happily burning hydrogen into helium in its core. And the M stars, the red dwarf stars like Proxima Centauri, 75% of the stars in the Milky Way are red dwarfs, M stars. They have enormous lifetimes, 20 billion, 200 billion years. Every M star ever born is still alive today. Okay? So we're going to come back to this in a moment, this idea. And what can an individual O star do? A really powerful one, like this one with the romantic name BD plus 60, 25, 22. This star is blowing a bubble. We call this the Bubble Nebula. And this O star is extraordinarily luminous and has a wind, 4 million miles per hour, radiation-driven wind. Okay, this is one heck of a wind. Okay, this is truly the Windy City. Okay, so what's going on here, this star, as it blows out this wind, and you can see the Bubble Nebula, you see the pillars again. This O star is excavating, helping to excavate with its wind, pushing out blowing open a hole inside this molecular cloud. And what we can do, once again with the wizards of Hubble, let's fly in and turn it around a bit. So once again, you see this kind of cavity in this nebula. And now we can get a sense of how just an individual O-star can shape the molecular cloud surrounding it and get an idea of the texture here. You may say, well, why isn't that star at the center of the bubble? Because in this direction here, it's pushing against a thicker interstellar matter regime. It doesn't get as far. But out here, whereas it's blown the cavity in this area, the bubble can expand more in that direction. Okay. So these are some of the things we've seen in the IS, in the interstellar medium, in these molecular clouds, watching the process of star formation and watching with these O-stars in particular, how they can shape it. All right. So how do we make, well, I forgot one other thing. Oh, one other thing. There's another really important thing that these O-stars can do. As I said, they don't live very long. And what happens to one of these O-stars when the way it makes nuclear fusion go in its core, when it runs out of fuel, something really explosive happens. The core of such a star, at the very last hour of its life, is about 1.5 to 2 solar masses of iron. And just like that, in less than a second, that core of iron that's the size of the Earth collapses to something the size of a city in a second. The interior of that star says, what the heck just happened? The core is gone. It goes down fast. And before you know it, oh, this is a video, sorry. It's more fun watching the video first. You see a big flash. A supernova occurs. O-stars blow up. Okay? And this is not a little itty-bitty explosion. These things are unbelievable explosions. Okay? And they can create, either by themselves or with the help of other O-stars nearby that also eventually blow up a supernova, they can carve huge holes in the interstellar medium, ranging from hundreds to up to 1,000 light years. Okay? This one is real. It's actually called the Crab Nebula. The Crab Nebula is a real thing in the constellation Taurus. It was at the supernova that created the Crab Nebula was charted by Chinese astronomers. It occurred on July 4th, 1054. Okay? And when we point our telescopes at that position today, we see this. This is the exploded innards of that star. And it's has a diameter of 11 light years at a distance of 6,500 light years. Why are these supernovae important? Essentially, all the oxygen in your body is created by explosions like this, supernovae. And they're bright when they occur. Even though it was 6,500 light years away, when it went off, this particular supernova could be seen during the day on Earth. Okay? And when you think about this and where the atoms come from and where the oxygen comes from, other atoms come from different sources. If someone asks how old you are, I say, oh, I'm 20 years old, I'm 30 years old, I'm 60 years old. The stuff that you're made of is much older than that. If you could interview the atoms in your body, we get an Enterprising Medill student, they could figure out how to talk to an oxygen atom in your body. Where did you come from? You get amazing stories. The oxygen atoms in your body were created by supernova explosions before the sun formed 4.6 billion years ago. They became incorporated in the solar nebula, ended up on Earth, and right now they're part of you. They'll go do something else when you're done with it. Okay? So you are composed. Carl Sagan, the famous astronomer, used to say, we are made of star stuff. He's exact. That's it. The stuff you're made of, the atoms in your body, come from these supernova explosions and other sources. All right. So I've been prattling on. How do we make sense of all this? Okay. This is, I mean, we're doing, what does this mean? How can I put this all together? It's almost like you find yourself in a room in a house and you're trapped and you're told, okay, you're in this room and you got one window. Describe the house. Well, fortunately for us, we have a window above and below the plane of the Milky Way. We can peer out, particularly with a wide variety of telescopes, but particularly the sharp eye of Hubble, and we can look at other galaxies because it turns out spiral galaxies are rather common. And when we look at other spiral galaxies, like this one in the constellation Centaurus, moving away from the plane of the Milky Way, we zoom in now with Hubble, and we can begin to see how these different pieces come together. We see this spiral structure, and we see these colors. And the colors we see these blues. The blue colors are what you'd expect from these very massive young stars, O stars and B stars. We see the pinks. The pinks are from nebulae that are excited by the ultraviolet radiation of these O and B stars, heating up the gas and causing it to glow at those wavelengths. We see the browns, the dust. We see the dust clouds. We see the connection between these dust clouds, the O stars, and these nebulae. And they're connected on these spiral arms. And we see this so beautifully with the Hubble telescope. We can see this structure in a nearby galaxy. Before Hubble, this was just a smudge. Okay? With Hubble, we can sharpen and see this stuff. And the way to think about this is the way this works in these spiral arms. When you think of spiral galaxies, what happens, they're rotating, vast rotating systems of stars, and over time, the dynamics of these disks lead to spiral density waves in the disks, where these spiral density waves don't rotate so fast, but as this gas rotates through in the disk of the galaxy along with the stars, it tends to slow down in these density waves and bunch up. When you bunch up the gas and dust, and it begins to collapse into stars. And you begin to make the stars that heat up the nebula, and you see them connecting here. And then everything keeps rotating, and since the O stars lead such short lives compared to the amount of time it takes to go around the galaxy, they disappear. Now, you can also see this. This is kind of a simulation. I admit this. Now, if I had you stare at this long enough, I could keep telling you, you like broccoli, you will eat broccoli in the morning. Okay, so this is like I keep staring at this. Oh yeah, okay. So don't get hypnotized by this. But this is one way to think about this, everything in the galaxy rotating around and goes through on these density waves. And the blues don't keep going because those O stars die out. Okay. The point is I'll stop this here before people really start eating broccoli. So let's move on. So the point is this is the way to think about how our galaxy, like these other spiral galaxies we see, are star factories. They're star-making machines, and the spiral structure you see has a lot to do with it. But that's not the only factor. And you can get a sense of that as well when you compare an optical picture of another spiral, M74, at a distance of 32 million light years with Hubble. And here you see the optical, and you see the same kind of structure, the dust and the blues from the O stars and the nebula. And here is with JWST, the Webb telescope, you focus just on the dust. And now you can see some of the structure in the dust. And you can see these giant holes that I talked about type 2 supernova blasting when they go off together. And that's another way you can make stars, is when these supernovae go off, boom, they carve out a hole, and they also push the interstellar matter together, and you create more stars. So these things so it's a kind of a complicated process between both of those effects and others. But it really, you can, with the combination of Hubble and Webb, and we're only beginning to really see this now, because remember, Webb's only been up there for 2.5 years, and it's only now beginning, a lot of these images are coming into play. But it's so powerful to combine the impact of both of these. Now, why bubbles like this are so interesting is right now the sun is traveling through a bubble, okay? Now, once again, astronomers are imaginative. We call this bubble the local bubble. We're traveling through the local bubble in the Milky Way. The local bubble is about 500 light years across. It was created by the supernova explosions of like 10 stars over the past 20 million years. And we've been in the local bubble for about 5 million years, moving across it. And that's great, because since we're in a local bubble, we have this view. We're not in the middle of a giant molecular cloud. We have a view of the surrounding galaxy, although it's limited to some extent, but we can see out. So that's, you begin to think that, well, when in the sun traveling around the Milky Way over its history, occasionally it's been in giant molecular clouds before. Now, one thing I've ignored up to now is, well, there's lots of spiral galaxies, so which one does the Milky Way look like? What does the Milky Way, what does its face look like? What does the face of the Milky Way look like? You say, well, we just launch a probe, we get a bird's eye view. No, that'd be one heck of a bird. We can't do that, it's just too far a distance. So we've been doing is, you try to sort out the Milky Way from looking inside of it, and we can do that pretty well now with Hubble and Webb and other kinds of telescopes. And look at a number of galaxies nearby. Which one, see there's this huge range of spiral galaxies. Sometimes they're inclined, from our point of view, but some have tiny centers, some have big centers with bars in the middle. Indeed, about 2/3 of spirals have these bars. And sometimes there's trouble. This one doesn't look happy. Something terrible is about to happen here. Something bad happened here. More about this one in a second. So our Milky Way really doesn't look like any of these. Where do we find one that does? And yeah, we have found one, okay? Among all the spirals that Hubble has looked at, the best bet that what our Milky Way looks like, if we could put a face on it, is something like this, with a reasonable bar and spiral arms that are kind of wound out some. And the sun lives close to one of these spiral arms. You say, wait a minute, what's this? Is this some kind of intergalactic? No, this isn't, we have these nasty asteroids. They're trouble even for Hubble. Kind of an asteroid wanders across your source. And since Hubble took this picture, multiple exposures over 4 orbits, that's why you see it cut up like this. So this is an intervening asteroid. We don't know its name. We don't know anything about it, but just kind of wandered in the path. But this is, among all the galaxies that Hubble's looked at, UGC 12158 is the one that seems to be most like Hubble. I mean, most like the Milky Way. Well, let's go back to the galaxy, that weird galaxy I was telling you about. Now, this is a photo taken from a ground-based telescope, and it just is weird. It's got these 2 kind of lobes and these amazing arms like this. What is this? This is a colliding galaxy. What? Galaxies can collide? You talk about the ultimate disaster movie, which has not been made to date. Colliding galaxies, okay? On a scale it's hard to even imagine. But this isn't something you can't, it's not like, oh, I went to the telescope tonight and I watched 2 galaxies collide. No, this takes time, billions of years. This collision started about 200 million years or so ago. And here are the centers of those 2 galaxies, here and here. And you notice we talked about seeing the signature of star formation going on. And here is a star burst. Okay, here what Hubble has taken this picture, and you see these intense blues and nebula and the dust. And the point is, you smash 2 galaxies together. The stars are spaced far enough apart, you could almost get 2 galaxies to pass through one another without actually any star-on-star collisions. But you can't forget about gravity and smashing clouds together too, the hydrodynamics associated with that. And so instead of the leisurely smashing clouds, clouds collapsing and making stars at a leisurely place in the Milky Way, here you smash clouds together violently at hundreds of kilometers per second, and in addition to the gas that gets thrown away from the galaxies, you smash the remaining gas together, and you make many, many more stars much, much faster than the Milky Way is. Indeed, these antenna galaxies right now are producing stars at a rate of hundreds and hundreds of stars per year, much, much faster than the Milky Way. So this is an amazing way to think about, I hadn't mentioned up to this point, but star formation in the traditional sense of with the spiral arms it's not a very efficient process. Out of only like a couple % of a cloud is made into stars before the cloud is blown away by winds and supernova explosions. Here is a way, by smashing galaxies together, you can actually turn that gas and dust into almost all stars very quickly with one fell swoop, one collision. You say, well, this must just be a rare event. No, this happens all the time. Hubble has taken hundreds and hundreds and hundreds of images of these interacting galaxies. This was another new thing with Hubble, because with this sharp vision, we could see this happening. Before, these were just blurs. We couldn't really make out the structure. But with Hubble, we can see these galaxies hitting each other and in this process of hitting each other. And once again, just like we talked about star formation, individual pictures pulling together a process. How does this work out over a collision process that can take billions of years? We have a better idea how this can happen. Now, just as another thing, I will have an aside here. We live in an expanding universe. The universe is expanding. Clusters of galaxies pull apart from one another. The point is, how do you get these collisions in the first place? Typically in clusters of galaxies where they're held together by their mutual gravity. There you can get these collisions. Okay. So, but we have nothing to worry about here, right? Well, there's always something. We live in a cluster of galaxies, but it's a very poor one. And it's called the local group, our local cluster. There's 3 spiral galaxies in it, big ones. Well, actually, 2 big ones, us, Milky Way, and Andromeda, the Andromeda galaxy, and another little spiral called M33 Triangulum. And there's another 50 or so, 100 galaxies, little ones that kind of orbit. The big spirals are just out there, okay? And here is a photo of Andromeda. And Andromeda is one of these things, if you go out, one of this dark site this summer, and you know where to look for Andromeda, you can see Andromeda with the naked eye. It's the only extragalactic object in the northern hemisphere you can see with the naked eye. It's a smudge, but you can see it. And it's far away. It's 2.5 million light years away. So why would we worry? It's moving toward the Milky Way right now at a velocity of about 120 kilometers per second, 120 times the speed of a rifle bullet. So what's going to happen? Well, by everything we've learned from these interacting galaxies in the process of stars collecting, we can come up with computer models and input everything we know, and we can figure this out. So let's go on an adventure on a computer. So here's our Milky Way, happily spinning away, and the clock has started from now, happily spinning. The Milky Way is just doing its own business, not paying attention, and then we look at the big picture. And here's Andromeda zooming in on us. M33 is like the kid brother just watching what's about to happen. So he's not going to participate. He's just going to watch this. And getting closer, clock is continuing to tick here. Getting stretched up by gravity. First pass, probably a miss. Push. Okay, well, we're fine. Well, no, gravity, when you get closer, it begins to work harder, and then boom, first pass. Okay, the kid brother's still out there watching, staying far away, And then another pass. And what's happening through these passes is the gas clouds in the galaxy are smashing into each other. A lot of the gas is being thrown away off into extragalactic space. A lot of the stars are thrown away into extragalactic space. The gas remaining between these two galaxies has been smashed, and you're converting it into stars in a starburst. And you notice how the color has changed. You don't see much blue in this combined galaxy anymore. You see the yellow. There's no more gas left in this combined galaxy. We've blown it away or converted it to stars. No more O-stars are going to form. Not much more interstellar matter. And that's what we're left with. So what would that look like from Earth? So here's today, and there's the Milky Way, and there's that smudge called Andromeda. And let's start the clock again. And you know what they say about things in your rearview mirror getting big, should be bigger than they appear. And as the clock ticks, Andromeda's getting bigger and bigger, and then we get the biggest fireworks display of all time. And it lasts for hundreds of millions of years. The entire sky explodes as we smash all the interstellar clouds together and have a starburst that ignites all the gas and dust in the Milky Way into stars. And then 7 billion years from now, the Milky Way that I urge you to see this summer is gone. The galaxy has been irrevocably changed. Now we have the center is the center. And that's where what's happened is the 100 million solar mass black hole at the center of Andromeda, and eventually the 4 million solar mass black hole will merge into one. This is the thing that Vicky's really good at, is smashing black holes together. So, but this is, and actually astronomers have come up with a name for this galaxy that will result from the merger of Andromeda and Milky Way. They call it Milkomeda, okay? And this is how happens to the Milky Way in the far future, we think, maybe. Okay, there's some variables, but this is one, and the Milky Way is gone. Okay, this is the future, and eventually, over many, many billions of years, eventually all the stars will go out. But that's another story for another time. The good news is, though, we still have plenty of time to study our Milky Way. Okay, and one of the best places to study it, it turns out, is in the South American country of Chile, which has amazingly dry weather, amazingly clear skies, and this is taken from the Atacama Desert in Chile. And this is where we're all excited at Sierra. The past 15 years have been so exciting, but the next 15 years also are even more exciting because the Giant Magellan Telescope is being built right now on a mountain just to the south of the Atacama Desert. And we will have this kind of sky to look at. And Sierra consists of all these amazing astronomers of all ages that are really excited to begin to use telescope like this. This telescope will consist of 7 8-meter diameter mirrors. Combined together will have the effective aperture of something like a 25-meter mirror. And it will be equipped with instrumentation that can take away that miserable smearing effect. And we get amazingly sharp views from the ground. So this will happen. This telescope will see first light, we hope, sometime in the 2030s. That's what's coming, and that's why so many of us in Sierra are really excited about. And so there'll be some time, hopefully 15 years from now, maybe less, where there'll be someone else here telling you all about the latest results with the Giant Magellan Telescope. For now, I just want to thank all of you for coming and thank all the folks at Sierra from whom I've learned so much over the years. Okay, that's it. Thank you.
We can take questions now. And there are,
So, who has questions?
you can talk on the mic. There will be people distributing mics, so raise your hand if you have questions. All right.
Yes, can you shout or do you need a mic right away?
We'll need the mic.
Okay.
What kind of temperature are we talking about here? I mean, is it still like super cold?
Do you mean in terms of the interstellar matter being red or blue?
Yeah, on the pictures that Hubble took, and they're colorized, they're blue and red and so forth.
It's one of the things to understand is that typically the color scheme that in those Hubble images, it depends on the situation. I mean, it is, when we look at Hubble of the same thing at different colors, we typically put filters on a telescope that look at particular wavelengths. And then it's when you actually, the key thing there is to get the structure in these images, okay? What kind of structure? And sometimes these filters are very narrow. That can be due to a particular atom. So for example, like the Crab Nebula supernova remnant I showed you, you can zoom on, oh, maybe oxygen was, what does oxygen look like? You can zoom in on that, give that a color, okay? So nebulae, you may have noticed some of the nebulae, they look kind of greenish, and other nebulae look red. That can be specifically due to hydrogen is red typically, and green can be kind of oxygen. But you can come up with different color schemes. Like in the infrared, when I showed you colors in infrared, we can't see colors in infrared. Now with the galaxies, though, when I showed you pictures of those galaxies, and you saw those pinks and blues and browns, that's real. That's what your eye would kind of see, okay? So that is real color. In the nebulae, sometimes you got to be careful. It may not look like that. Typically, nebulae will look reddish due to this hydrogen emission. Okay, question?
Hi, this was very cool. What one thing about your work keeps you up at night?
What one thing about my work keeps me up at night? Wow. Well, actually, it keeps me excited because I'm retired now, okay? And one thing is when I was not retired, I had a busy trying to write papers and get grant money and teach, and I have to do that. But what I did when I was busy, I found these research rabbit holes, I call them. Boy, that's weird. I don't have time to do that now. I got to do this and teach class. Okay, I'll write it down now. So I got this long list of rabbit holes, and now that I'm retired, I can go into the rabbit holes. And most of them are just rabbit holes, but some of them, some really cool stuff. Wow, who would have thought that? And that's what I'm working on. And sometimes what I found when I sleep at night, if I begin working on it in the evening, and then I let my subconscious brain go to work because what's going on? In the morning, oh, that's what's going on. So it doesn't keep me, I use going to bed at night to help me work through these problems. It's not a bad thing, it's a good thing. Other questions, come on.
I have a question.
Where are the aliens? What?
Going back to the Andromeda galaxy coming towards the Milky Way, is the Milky Way standing still?
Oh, that's a great question. Yeah. That's a great question. Nothing is standing still in the universe, okay? And what's the ultimate reference frame to compare things to, okay? We're moving, I mean, there's kind of an ultimate reference frame. It's the radiation glow left from the rate of the Big Bang. We can sync up to that. And actually, with respect to that cosmic reference frame, the Milky Way is moving something like 650 kilometers per second, okay? And we kind of work out all these other velocities due to other things, okay? But and you're going places too that people don't really realize. It's really important to understand this. I mean, particularly if you ever tell somebody, oh, I'm just stuck, I never go anywhere. No. The Earth rotates at a speed of 1 kilometer per second. The Earth goes around the speed at 30 kilometers per second. It goes around the sun at 30 kilometers per second. And the solar system goes around the Milky Way at a speed of 220 kilometers per second, 220 times the speed of a rifle bullet. So you're going places fast. You're just not really going anywhere special because we're in this big local bubble right now. Okay. Up there? Up there, up there.
I don't need it. I think I can ask.
Okay.
Maybe this is like a silly question, but how long does it take to get those beautiful photos that
No,
you
that-
were showing us of like the pillars of creation? Like, is it many things coming together to make that one photo?
Oh, it can take quite a while. Now, it doesn't take outrageously long for that nebula, the pillars of creation, because it's relatively close and relatively bright. So, but Hubble has this problem because it orbits the Earth every 96 minutes, and it's got you can't let the Earth get in the way of the sun because it would fry the instruments. So you only get a fraction of an orbit actually get data. And so it can take multiple orbits to piece it together. And that's one of the things when you observe with Hubble, we've got an observing plan, sorting out, you want to optimize it as much as possible. Indeed, the way Hubble works is all the observations that are planned for a year, they all go into a supercomputer to try and plan the most optimal way to do this. Because Hubble doesn't move fast. It moves as fast as the minute hand on a clock. It takes 30 minutes for Hubble to go from here to here. You don't want to waste Hubble's time moving all the time. So it's like the ultimate traveling salesman problem. How do you take all those trips to all these places in the sky in the minimum amount of time? And you try to cut it so you want to expose as long as you can. You want to get as much data as you can, but you don't want to waste time. So the typical, on a lot of these photos of like the nebulae, they're with Hubble maybe a few orbits, a few hours. Hubble's it's a reasonable sized telescope, and the key thing is the sharpness that you get out of Hubble. Those kinds of images are really hard to do from the ground.
When should we come back to see Saturn through the telescope?
I don't remember exactly when. It'll be sometime this summer. I don't know exactly off the top of my head. It's a kind of thing now, since we've got AI online, you just ask, go to Google, say, when will Saturn be observable in the early evening from Chicago? Let's see, and you'll get the answer. Okay, that's a good way to go. Okay, he has his hand up.
Thanks. What determines what kind of, when a star forms, what determines what kind of star it's going to become?
Okay, that's another great question. That's a great question. It depends. A key part is how massive that cloud is, how much mass is there. And some of it's somewhat variable. Now, it turns out the most massive stars, it takes the shorter amount of time. They can form in less than 1 million years easily. The less massive stars appear to take longer. There are some clouds where only relatively low mass stars form. Other clouds have these more massive stars. I'm not enough of an expert on star formation. I mean, exactly how does that work for each one? In other words, I guess what I'm trying to say is you won't necessarily get the same assortment of different stellar masses in a different clouds, in the cloud from cloud to cloud. It's just that these clouds in particular that make the really massive stars, they tend to be the most massive clouds. In terms of messing up the ISM, it's usually these O stars are the most dynamic ones. Okay, he's had his hand up right there.
I call myself an amateur astronomer, and I'm really into practice. I practice astrophotography, so I have taken images of things in deep space, which is my favorite. So the Orion Nebula, I can clearly see the gas clouds, and I take images with my camera. But I've always wanted to do more. I don't want to just take pictures. I want to learn about the universe using my own images, using my own equipment. So is there anything that you can think of that I or people like me with our own at-home equipment can learn about the universe using our own methods?
Okay, I may be somewhat biased here, but oftentimes when you're trying to think what needs to be done, okay? And one of the key advantages if you got instrument that can take wide field views of the sky, maybe not going to the densest molecular clouds, but looking at regions where people say there's nothing substantial there, okay? And doing deep, like H-alpha hydrogen observations to pull out these very faint nebulae, gas clouds that out in the above the plane of the galaxy in the halo, and understanding where this gas comes from. That's one of the things I'm looking into now. And it turns out we don't know that much about that regime. And indeed, actually, this is kind of almost astonishing to believe, a molecular cloud, not a really massive one, but a respectable one. The closest molecular cloud was recently found 2 weeks ago. It was staring at us right in the face. No one noticed it before because it was spread out over a reasonable big chunk of the sky. There wasn't much there. It didn't have massive stars inside. So how do you find such a thing? And so the point is these tracers and looking at, in other words, look where there don't appear to be any clouds and see if you find some. And actually that's what amateurs, this is where amateurs are taking the lead. They have the equipment, they have the time, and they just take these long, I'm talking weeks and weeks of exposure time and see what you can bring out of the darkness of space. That's something that professional astronomers are not doing, and where amateur astronomers can make a real difference. Other folks, yes?
What evidence of dark matter do we see in our own?
You notice that I carefully avoided dark matter in this story. Okay. See, if I focus on the stuff we can see, then I sound like I really know what's going on, okay? But if I tell you, well, dark matter, most of the universe is made out of dark matter, we don't know what it is. And the universe is governed by this thing called dark energy, and we don't really know what that is. Then, well, what if you don't? I won't go there, okay? But the point is that we believe that the Milky Way is mostly dark matter in terms of matter, but it's spread out in a halo around the galaxy, okay? And we believe that most galaxies, essentially all galaxies in the universe, have these dark matter halos. Dark matter, unlike the matter we're made out of, tends not to bunch up into little things and make stars and planets. But it guides, we find that the matter we're made out of, which can do that, we find that in the middle of these dark matter patches in the universe. Okay, and so the dark matter is extremely important. Dark energy is extremely important. They seem to govern the evolution of the universe on a large scale. It's an active field of research, and we've got a lot of scientists studying. It's amazing what you can learn about something without knowing what it is. Okay, I decided long ago not to go in that direction.
We will take one more question, but Dave will be sitting at the Sierra table outside. So Dave chooses the last question.
His question right there.
What was the coolest thing you got to research?
What's the coolest thing What's the coolest? I couldn't hear. I'm sorry.
That you ever
What's the
got
coolest
to
thing I got to research? Wow. Okay, it is. Now this may not be as cool. Not everybody think this is cool, but getting observing time on even ground-based telescopes, big ground-based telescopes, is tough. And I've always had this. I'm kind of a risk taker. You have to plan way ahead of time to get telescope time, like nights and nights in a week on a big telescope like in Arizona. And you've got plans of what you're supposed to do. You have to write a proposal. This is what I'm going to do. But I always hope for is a bright supernova goes off in another galaxy. And then I can use it as a light bulb to study the gas between me and that supernova. So long ago, back in 1993, this wish came through. Like 2 days before I went to the 4-meter telescope at Kitt Peak in Arizona, boom, supernova 1993J blew up in the nearby galaxy Messier 81. Wow, what a great break. So I just spent the entire 4 nights, it was absolutely clear out front, and I just sat taking these beautiful spectra of this supernova. Now, what I did was being uber paranoid. This was at a time when we put data on 9-track tapes with mag tape drives, and they said, oh, do this at the end of your observing run. I said, no, I have to be careful. I will do it at the end of each night. And it was good I did, because they were just beginning to experiment with microwave data links from telescope headquarters in Tucson to the mountain. And somebody messing around the morning after I completed my run deleted all the data that I had on the computer. If I hadn't backed it up put on these mag tapes, I'd have lost the whole thing. Okay, it pays to be careful.
So before we thank Dave, you can ask him more questions. He'll be at the Sierra table outside. Walks in groups are starting now to Dearborn Observatory. There will be a round of trivia that will happen in this room if you want to stick around for that. And remember to fill in the surveys, and if you do something a little extra, you will get